We have talked so far about energy sources that can be connected in an electric circuit. Now, in this lecture, we are going to talk about a new definition, which is the resistance. And this is of course related to our first passive element, the resistor. In physics, we have two types of materials. The first type, which is the conductors. These are materials in which charges can move easily inside them, however, cannot easily move away from them. A good example of conductors is the copper. These materials are said to have low resistance, since they allow the passage of charges inside them more easily without being resisted. So the passage of current inside them is easier. The second type of materials is the insulators. These are materials in which charges cannot move easily inside them. A good example is the glass, where current cannot pass through glass. These materials are said to have high resistance since they highly resist the passage of current inside them. Now, the most important and used law when talking about resistance is the Ohm's law. Experiments show that for many conducting materials, the current passing from one end of this material to the other end is proportional to the voltage across its ends, where R, the resistance of the material, is the constant of proportionality. Now, writing this in the form of an equation, we can write V, which is the voltage, is equal to R, the resistance of the material, multiplied by I, the current traversing this material. Rearranging this equation, we can write R in terms of V and I, where the resistance is equal to voltage divided by the current. The unit of resistance is ohms, and it is symbolized as written here. Virtually all devices and equipment have inherent resistance. Each material can be conducting or insulating. It can have a low resistance or high resistance, and this is what we call the inherent resistance, which means the material has its own resistance. However, a circuit element which is designed specifically to have resistance is called a resistor. There are two circuit symbols commonly used for resistor. The first one is this one, and the second one is this one. Here is a picture showing a real resistor that is used in circuits. Resistors, as well as other components, can be connected in different ways in a given circuit. The first way of connection is the series connection. If the components or the resistors are connected end to end, forming a single path for the current as shown in this figure, this means the connection is series connection. As you can see in this figure, we have a voltage source supplying a voltage V and current I to the circuit. This current I passes through R1, then continues through this single path over here to pass through R2, then continues to pass through R3. There is no other path that I can pass through instead of this path through the resistors. Since R1, R2, and R3 are having the same current I passing through them, this means that R1, R2, and R3 are connected in series. Now let's write some equations. If we need to look to the voltage between the points A and B, which is UAB, we can look to the circuit in this direction, where UAB is equal to the voltage across the voltage source. So we can write UAB is equal to V. We can also look to the voltage between the points A and B in this direction, where the voltage between these 2 points is equal to the voltage across the resistors R1, R2, and R3. So we can write that UAB is equal to U1, the voltage across R1, plus U2, the voltage across R2, plus U3, the voltage across R3. Applying Ohm's law, we can write that U1 is equal to I, the current passing through R1, multiplied by R1, the resistance of the resistor R1. Similarly, U2 is equal IR2 and U3 is equal IR3. Now taking I in common, we can write that UAB is equal to I into R1 plus R2 plus R3. Now there's something that we call an equivalent resistance or equivalent resistor. Equivalent resistor means a resistor that can replace a number of resistors where this resistor will have the same current passing through it for the same applied voltage. Looking into this circuit, an equivalent resistor that would replace the resistors R1, R2, and R3 should have the same current I when the same voltage V is applied. Looking into this equation, UAB, which is also equal to V, is equal to I into R1 plus R2 plus R3. Then, the resistor that will have the same current I under the same voltage UAB should have a resistance of value R1 plus R2 plus R3. Now in general, if we have n number of resistors that are connected in series, we can write the equivalent resistance, which will have the value of R equivalent is equal to the sum of all the individual resistances. So R equivalent will be equal to R1 plus R2 until reaching Rn. When talking about resistors that are connected in series, we are talking about voltage divider circuit, where we can use the voltage division rule. Suppose that we have this circuit over here where R1 and R2 are connected in series, and we have a voltage source that is supplying voltage V and current I to this circuit. The voltage division rule gives us the value of the ratio of the voltage across one of the resistors, which is V1 or V2, over the total voltage that is supplied to this circuit. We know that the value of the voltage V1 by Ohm's law is equal to I, the current passing through R1, multiplied by the resistance R1. Similarly, V2 is equal to I multiplied by R2. And the value of V is equal to V1 plus V2, which is IR1 plus IR2. Taking I in common, we obtain that V is equal to I into R1 plus R2. Writing the ratio, V1 over V is equal to IR1 over I into R1 plus R2. Eliminating I, we can write V1 over V is equal to R1 over R1 plus R2. Note that the resistors R1 and R2 are connected in series, so R1 plus R2 is equal to the value of the equivalent resistor of both resistors. This is simply the voltage division rule, where the ratio V1 over V is equal to R1 over R equivalent. The general rule for voltage division is VI, whatever the value of I was, over V is equal to Ri over R equivalent. For example, if we take resistor R2, then I is equal to 2. So V2 over V is equal to R2 over R equivalent.